Hello and welcome back. So in the previous lecture, we are trying to calculate various thermodynamic properties using G over RT as the generating function. And once we have an expression for G over RT, the Gibbs free energy, in terms of the compressibility factor Z and measurable quantities such as PV and T, we have derived relations as to how G over RT is related to these, and then for the other thermodynamic properties, you can use the expressions given here to relate them to the measurable quantities. For example, since dG is VdP minus SdT, remember we said we like this expression because the Gibbs free energy change is expressed as a function of temperature and pressure, or changes in temperature and pressure, which are readily measurable in a laboratory. So dG is a convenient function to work with in that sense. And once we have an expression for dG over RT, we can rewrite it, eliminate S and rewrite it in terms of V and H. And the partial derivatives of G over RT with respect to P and T are given over here. And if I have a relation for G in terms of PV and T, then I can use these equations here to calculate all the thermodynamic quantities I'm interested in. Then we have defined what are known as residual properties. We define the residual property, any residual property, Mr, as M minus Mig, everything taken at the same temperature and pressure conditions. So Ig stands for the ideal gas condition, R for the residual property, and M is the total property. So once we have that relation, we can express various residual properties, Vr, Hr, Sr, and Gr, in terms of the compressibility factor Z, T, and P essentially. And in expressions for the entropy and the Gibbs free energy, there appears a constant J. And we have shown yesterday that this constant J is independent of temperature, and in most cases I'm interested in delta of these quantities, so it doesn't matter what that value of J is going to be, I can arbitrarily set it to 0, so we're going to ignore that J from now on. So we had expressions for HR, SR, and GR, and once I have that, I can calculate total property or add this to the ideal gas value to get the total property. It turns out that the residual properties are convenient, right? It is convenient, and they act as corrections to the calculations based on ideal gas properties, right? So for example, if I have a residual volume, it is a correction over the ideal gas volume. If I know the ideal gas volume, I can add the residual volume to get the total volume. So this is sort of a correction, and for gases it works out because most of these corrections are usually small. Major contribution comes from the ideal gas value, and then you have a small correction on top of that to get to the total property. And this holds for all the other properties as well, H, S, etc. Right? On the other hand, for liquids, these corrections become pretty large because there is vaporization, enthalpy of vaporization is pretty large, so it might not be as convenient, but definitely for non-ideal gases, if they do not obey ideal gas law, then I can always use the residual property and use it as a correction over the ideal gas value. And again, these residual properties are going to be related to the PVT or the compressibility factors as we have derived the equations previously. What we're going to do next is look at some of the more common approaches for obtaining the compressibility factor or the PVT relationships. One of the easiest one to relate the PVT quantities in a gas is through what is known as Virial equation of state. So equation of state usually is a term we use in thermodynamics for PVT relationship. How one of them is related to the other two values. Now, when we talked about the ideal gas early on in this course, we looked at virial equation of state, and we said that it is sort of a power series expression for PV relationship. So for example, what we said is the product PV can be expressed as A plus BP plus CP squared, etc., right? And if I factor out A, it would be 1 plus B prime P plus C prime P squared plus so on. This is an infinite power series in terms of P. For an ideal gas, only the first term is sufficient, and we have already seen that this value of A is going to be equal to RT. All the subsequent terms drop out for an ideal gas, but if the gas is not ideal, then we're going to use as many terms as they are necessary to express this product PV, right? So the other way of writing this is PV over, I will bring that A to the other side, or RT to the other side, so that this will be 1 plus B prime P plus C prime P squared plus so on, right? And these quantities here are known as the virial coefficients, right? This is power series in P. An equivalent expression can be written for power series in terms of V. So the coefficient is going to change. We'll replace B prime with B and C prime with C over V squared plus so on. And in fact, these quantities are related. B prime is going to be equal to B over RT. C prime is going to be equal to C minus B squared over RT whole squared, and so on. Those equations can be derived, but the main idea of this is that I'm expressing this PV term as a power series in P, or in other words, I'm expressing this quantity PV over RT as 1 plus B prime P plus C prime P squared, etc. And recall that PV over RT is what we called as the compressibility factor. For an ideal gas, it will simply be 1. If the gas is non-ideal, then we'll have the additional terms in these power series. Now, which one of these two forms is better? It turns out that if there is only one term we are going to use in addition to the ideal gas, so for example, if I'm going to use only B, then PV over RT is 1 plus B prime P, or in terms of B it is 1 plus BP over RT. This equation is convenient and same accuracy. It has the same accuracy as that of Z is 1 plus B by V. On the other hand, if I need more than one term in P, then it turns out the second form, which is this, is a better, it has better accuracy. Now, let's give some names here. We call this B as the second virial coefficient. This is a virial equation of state, so B is the second virial coefficient. This C here is what we call as the third virial coefficient. Depending on the requirement, we will use either one or two terms. Higher order terms are rarely used. It is very difficult to obtain B, even C it is very difficult to obtain. So any term higher than C cannot be obtained experimentally. So it doesn't make sense to be using higher order terms. At most, for practical applications, we're going to use the second virial coefficient or maybe the third virial coefficient, depending on the requirement, if the pressures are a little higher. At moderate pressures, second virial coefficient usually works. And again, like I said, the form of the equation for virial expression we will use will depend on how many terms I'm using. If I'm going to use only the second virial coefficient, then this equation here is enough. If I'm going to use both the second and the third virial coefficients, then we will use this equation. The essential difference is, if you see on the right hand side, in the first case, in this case here, there is only P and T. In the second case, there is volume. So one of them is explicit in terms of pressure, the other one is explicit in terms of volume. So if I don't know volume, I will have to solve the cubic equation in the second case, but in the first case it is a straightforward calculation. Well, if it is a power series expansion, how do these curves look like? So let's take an example. This is methane at 4 different temperatures, and what we are plotting on y-axis is the compressibility factor for methane at 4 different temperatures from 200 to 320 Kelvin and going from pressure of 0 to 200 bar. The curve that is at the bottom, well, first, this point here is essentially the compressibility factor at the 0 pressure limit. All gases have to reach the ideal gas limit, so the compressibility factor value will be 1. So all of them start right there. At the highest temperature, the compressibility factors are closer to 1, as you see with this yellow curve here, whereas at the as the temperature decreases, the compressibility factor value is going to move farther away from 1, indicating more and more non-ideality. Remember, Z equal to 1 is the ideal gas limit. So as I move away from this value of 1, it means the gas is more and more non-ideal, right? So as the temperature increases, the gas non-ideality increases as well. Then there are other things we can notice from this curve. For example, we said we can express the compressibility factor Z as 1 plus BP over RT if I'm going to use only the second virial coefficient. So if you plot this curve or this expression 1 plus BP over RT, if B is not a function of temperature, not a function of pressure, then this should be a straight line, and this is obeyed only until moderate pressures. And as you can see, fairly until this limit for these gases, and maybe until that point for this gas, the part of that curve until those pressures is fairly linear. So the second virial coefficient is going to be sufficient to define or to fit the behavior of the gases until the pressures indicated. Of course, it changes with temperature, right? So for example, at 200 Kelvin, I would use only the second term if I have to predict the behavior until about maybe 30 bar, right? But at a higher temperature, of course, I can push that pressure a little bit more, maybe until 50 bar, and I could still use only the second virial coefficient and get away with it. So if this is the experimental data and one wants to estimate the second virial coefficient, how do I get that? All we need to do is simply take the derivative of this curve, dou Z over dou P at constant temperature, and take the derivative not at any condition, but as you approach at the lower pressure limit. So at the low pressure limit or limit as P goes to 0, if you take this derivative, then that will give you the value of the second virial coefficient. So another way of defining second virial coefficient is it is the derivative of compressibility factor with respect to pressure, right, at constant temperature, of course, and then let's rewrite that. It is the derivative at the 0 pressure limit for Z over P as at constant temperature. That is the second virial coefficient, right? Now, let us use these ideas and see if we can solve one quick problem. What we are given is the second and third virial coefficients for methane at 300 Kelvin, and we want to estimate the molar volume and the compressibility factor for methane at 100 bar using the following approaches. First is an ideal gas law, then we want to use only the second virial coefficient, and then we want to use both the second and third virial coefficient. So let's see if I can estimate the molar volumes and compressibility factors for methane in this scenario. I'm given the pressure, it is 100 bar, and the temperature is 300 Kelvin. If it is an ideal gas, then PV is RT, or the molar volume V is going to be equal to RT over P. And recall that R is 83.14 bar centimeter cube per mole Kelvin times 300 Kelvin over the pressure is 100 bar. So if we simplify this number, then let's call this as ideal gas volume, so VIG. If I simplify that, what I get is 249.2 centimeter cube per mole. This is case A. Now for case B, I want to use the second virial coefficient alone. Z is 1 plus BP over RT. So we'll first estimate the compressibility factor using the second virial coefficient alone. So it's going to be 1 plus, the value for B is negative 42.2 centimeter cube per mole times 100 bar over RT, 83.14 bar cc per mole per Kelvin times 300 Kelvin, right? And then if you simplify these numbers, bar centimeter cube per mole Kelvin times 300 Kelvin. And if you simplify these numbers, it turns out that the value of Z is going to be 0.8308. So remember, Z for an ideal gas is 1, but at these conditions, if I use the second virial coefficient, I end up with a compressibility factor of 0.83, right, which means it is 17% lower. And the actual volume then, using this value of compressibility factor, is going to be Z RT over P. Remember, RT over P is anyway VIG, so this is also going to be equal to Z times VIG. So that will be 83% of what we have calculated as the ideal gas volume, and that number turns out to be 207.2 centimeter cube per mole. So our molar volume actually is lower by using the non-ideal equation of state. In this case, we have used a virial equation of state with the second virial coefficient. And the third one, we want to use both the second and the third virial coefficients. So the form of the equation we should be using is this: Z is 1 plus B over V plus C over V squared. The values are given to us, but I have to solve this for volume. So what we'll do is rewrite the compressibility factor as PV over RT is 1 plus B over V plus C over V squared. And if you look at this equation, now you'll realize that everything in this equation is known except the volume. This is 100 bar times the volume over 83.14 times 300. Just make sure that we're using the correct consistent set of units. Negative 42.2 centimeter cube per mole over V plus the value for C was 2409. So 2409 over V squared. So now I have to solve this equation. This would be a cubic in V. Everything except V is known. I could use any suitable software, Excel maybe, and then get what the value of V is going to be. And in this case, that V turns out to be 213.28 centimeter cube per mole. If I want to calculate Z, it's going to be 213.28 over the ideal gas value, which is 249.2 at this condition. But the value of V now, as you see, is different from what we have calculated then. Let's list that. Ideal gas value, just the B, both B and C. Ideal gas was 249.2. Just using the second virial coefficient was 207.2. Using both B and C, it is 213.28. All of them in centimeter cube per mole. As you can see, each one will give us a different result depending on our experience and what we know about the gas and its behavior. We should be choosing the correct form of the expression we have to use for the particular condition. This is how we'll use the virial equation of state to calculate the molar volume. What we're going to do next is try to derive some expressions for the residual properties and then enhance the total property changes, and how we can use this information to calculate the total property changes from virial equation of state. So first, let us see or derive some expressions for residual properties using virial equation of state. We'll restrict our discussion only to the second virial coefficient. So the form of the equation we will use is the compressibility factor is 1 plus Bp over RT. Remember the equation we derived yesterday, that the Gibbs free energy GR over RT, the residual Gibbs free energy, is integral 0 to P z minus 1 by P dP. And now I know that the compressibility factor from virial equation of state is given by this expression. So I can write z minus 1 over P to be B over RT, which implies GR over RT is going to be integral of 0 to P B over RT dP. The second virial coefficient, we can show this rigorously from statistical thermodynamics. It depends only on temperature. It is independent of pressure. So I can bring everything within the integral sign out of that. So it will be B over RT integral 0 to P dP, or BP over RT. This is the expression for GR over RT. Now for HR over RT, we will use GR over RT as generating function. Recall that the derivative of this guy, GR over RT, with respect to temperature at constant pressure is negative HR over RT squared. Then HR over RT is negative T, right, times the derivative of GR over RT with respect to temperature at constant pressure. Now the pressure is constant, so let us use this expression for GR over RT right here and put it here and try to take the derivative. What happens is negative T, the derivative of Bp over RT with respect to T at constant pressure. So I can bring, because P is constant, I can bring P and R out of that derivative. So it will be Pt over R, and the derivative of B over T with respect to T. Pressure is constant, that's obvious, right? And this value right here, Pt over R, derivative of B over T is going to be 1 over T derivative of B with respect to T, right, minus B over T squared. That will be the derivative, right? Notice that I got rid of the partial derivative because B is only a function of temperature, so I can write just dB over dt. And then if I simplify this, it will be P over R times B by T minus dB by dt. This is the expression for HR by RT. So this is the expression for HR by RT. Now once I have HR by RT and GR by RT, SR is pretty easy to calculate. It turns out that SR over R is HR minus GR by RT. I have both HR and GR from the previous slide. One of them is P by R, B by T, dB by dt. P by R, B by T minus dB by dt, that's HR by RT minus BP by RT. That's GR by RT. So it turns out that the two terms cancel, and all I have left is minus P over R dB dt. All right, so that's the expression for SR over R. Then it turns out I can derive similar expressions for UR and AR. Then boils down to is I can express all the thermodynamic quantities only as if I know what the second virial coefficient B is and how it varies with temperature, what is dB over dt. If I have these two pieces of information, I can get all the residual properties. Can be obtained. And once I have the residual properties and I have the ideal gas specific heat, then I can calculate all the property changes that are of interest. So then the next thing to ask is how the second virial coefficient changes with temperature. This is second virial coefficient for water, and as you can see, usually it does vary with temperature in some sort of a power series. Depending on the compound we have, there are several expressions that we can use. The most convenient one is a polynomial either in T or 1 over T, more often the case, 1 over T squared, etc. And as you see here, B is written as this sigma over T squared plus sigma 1 over T plus sigma naught, right? Sigma 2 over T squared plus sigma 1 over T plus sigma naught, and the values of sigma are given here. Those are the values of sigma 2, sigma 1, and sigma naught. And once I have this, I can readily differentiate this equation, dB over dt, right? I can readily differentiate this equation to get dB over dt, right? So it will be negative sigma 1 over T squared minus 2 sigma 2 over T cubed. That would be dB over dt. So if I know an expression for B with temperature, then I can do a differentiation, get dB by dt and all the other information I need. So let's use this idea and try to solve a problem. A substance undergoes a change of state from an initial condition, a temperature of 398.15 Kelvin, to a final, and a pressure of course at 2 bar, to a final condition. T2 is 523.15 Kelvin and P2 is 3 bar. This is the change of state. The specific heat capacity for the substance in its ideal gas state is given. CpIg over R is given as A plus Bt plus D over T square. Values of A, B, and D are given to us. And its second virial coefficient is given. What we want to calculate is delta H and delta S. First thing we want to do is use an ideal gas law to calculate these changes. So I'm interested in delta Hij. As you recall, delta Hij for an ideal gas, delta A or H is only a function of temperature. So in this case, delta Hij is simply going to be Cpig dt, integral of that quantity from T1 to T2. And that value is easy to obtain. Cpig over R is given to us. So it's going to be R times integral T1 to T2 A plus Bt plus D over T squared dt. And this value right here is R A T2 minus T1 plus B over 2 T2 squared minus T1 squared minus D 1 by T2 minus 1 by T1. Now if I can simplify this equation, I can get what the value of delta Hij is going to be. What I get is about 4300 joules per mole. So ideal gas value is fairly easy to calculate if I know the ideal gas specific heat capacity, because enthalpy depends only on CPIG, or temperature in this case. If I'm interested in calculating the entropy change for an ideal gas, recall the expression. It's going to be integral T1 to T2 CPIG by T dt minus R ln P2 over P1. This was the expression for change in entropy of an ideal gas. We can run through the calculation similar to the integral we have done earlier for enthalpy, and in this case we can get the value to be about 6.15 joule per mole Kelvin, right? So those two are pretty straightforward to calculate. Now if I'm interested in using a virial equation of state, as the next part of the problem asks, right, use a virial equation of state to calculate the changes in enthalpy and entropy. How are we going to do that? Remember, by definition, HR is H minus HIG, which means H is going to be HR plus HIG, or delta H, the change in entropy or enthalpy, is going to be the change in the residual values of enthalpy plus the change in the enthalpy under ideal gas conditions. We have already calculated the change in enthalpy under ideal gas conditions. It was 4,300 joules per mole. So if I were to calculate the total enthalpy change, then all I need is to calculate the difference in the residuals between the initial and the final states, or delta HR. So delta HR is what I'm looking for right now, which is H2R minus H1R, difference between the final and the initial states. And I'm going to use virial equation of state to calculate these residual quantities, And remember, from a virial equation of state, HR was P over R, right, or HR over RT rather, was P over R, B by T minus dB by dt, B by T minus dB by dt. I need to calculate B and dB by dt at the initial and the final conditions. Then I can plug those numbers here to get HR over RT, or HR. What I'll do is calculate B and dB by dt at the initial and final conditions. Let me do that here. B is given to me. It's sigma 2 over T square plus sigma 1 over T plus sigma naught. The values of sigmas are given in the problem statement, right? If this is this, then dB by dt, like I said earlier, is 2 sigma 2 over T cubed minus sigma 1 over T squared. Once I have these two expressions and I have the values of sigmas given to me, sigma 2, sigma 1, and sigma naught, I can use these three values of sigmas here and calculate at the initial and the final conditions. I can calculate both the quantities I require at the initial and the final conditions. The initial temperature is through 398.15 Kelvin. The final temperature is 523.15 Kelvin. The B, this is T. The B is at this temperature, the value of B we calculate is negative 353.3 centimeter cube per mole. At the second temperature, at the higher temperature, it's slightly lower, it's negative 158.3. And dB over dt, at the first temperature, it is 3.63 centimeter cube per mole Kelvin. And at the second temperature, it's 0.27, right? So I can use the given values of sigma, and based on the expressions for virial equation of state, I can calculate what the values of B and dB over dt are. Once I have B and dB over dt, all that is left is to come back and calculate HR at the first and the second conditions. This is going to be, let's write expression out for the first condition at least. HR at the first pressure or the first condition, the pressure is given to us. It is 2 bar and the final pressure is 3 bar. So this is 2 bar. So 2 into 10 power 5 pascals over 8.314 joule per mole Kelvin is the value of R. Remember, now I'm converting everything into SI units to be consistent, so I have to convert B into meter cube per mole. So it's going to be negative 353.3 into 10 power negative 6 meter cube per mole. The 10 power negative 6 is to convert cc per mole to meter cube per mole over the temperature in the first at the first condition. So I'm going to write it. This is the first condition is 398.15 Kelvin minus dB over dt is 3.63 over, that is 3.63, and again it's centimeter cube per mole Kelvin, so it's going to be 10 power minus 6 centimeter cube per mole Kelvin. Oh, since we have put 10 power minus 6, it's going to be meter cube per mole Kelvin. So this is meter cube per mole, this is Kelvin, this is meter cube per mole Kelvin, and then everything else balances out here. I can calculate HR over RT. So notice that if I do not involve the corrections using the Virial equation of state, then I would have calculated only the ideal gas value, which is the negative 4300 joules per mole. And if I use the correction, then I add another 270 to that, which is about, what, 6% higher. So the estimate for enthalpy change is about 6% higher in this case. And for a process, that is a lot. If it is energy requirement for a process, then it's essentially 6% more. So these corrections are necessary for process calculations depending on how far away I'm from ideality. And we can accomplish this by using the residual properties and an appropriate equation of state. In this example, we have used ideal gas equation of state. I can run through a similar calculation for the entropy change, right? And in fact, all the other thermodynamic quantities, delta S is going to be delta S for the ideal gas plus delta S in the residual property. And remember, we have calculated delta S for the ideal gas already earlier, and we said that value is 6.15 joule per mole Kelvin. What I have left is to calculate delta SR, right? And delta SR will calculate it by calculating the residual properties at the first and the second conditions, right? And remember, we said SR over R is negative P by R dB by dt. So I can use this, calculate SR at condition 1 is negative. The pressure, initial pressure I have is 2 bar, so 2 into 10 power 5 Pascal over 8.314 joule per mole per Kelvin. A negative of that multiplied with dB over dt is 3.63 into 10 power minus 6 to correct centimeter cube to meter cube. This is S1 over R, and this value turns out to be negative 0.73. In these examples we looked at today, what we have done is use the idea of the residual properties and employed Virial equation of state to calculate property changes in a process. When we come back to tomorrow, we're going to look at other types of equation of state I can use to achieve the same objective. Thank you.